All right, welcome, ladies and gentlemen, to lesson 2 of Unit 4, looking at what's called implicit differentiation. So what we're going to do now is, instead of working fully with simple functions like the square root, the rational function, and all that, we're going to try to take the derivative of non-functions, or things that we can call implicit functions, or functions that are defined implicitly. And what an implicitly defined function is one that is not just a function of x. So we get x cubed plus y cubed minus 9xy. Well, this we can't really write as a function of y. And if we looked at this graphically, it would look a little bit something like this. So we get this function that looks like this, or actually this graph that looks like this is a non-function. We could actually separate it into, I think, 3 different equations to make a function, something that would come down along this line here, right up to about this point. Then we can go from this point all the way to the 0, and from the 0 all the way to infinity. And we could set up 3 different equations, but it's not really a very handy thing to be able to do. So what we want to do is we want to be able to take the derivative of this without needing implicit functions. That's why it's called implicit differentiation. Now this function is differentiable. We can find the slope. If you think of that graph, you can find the slope at every single one of the points. The slopes are all defined except for there's one vertical slope that we can't do. Actually, there's 2 vertical slopes we can't do. So this is now going to get into our implicit differentiation. What we're going to do is we're going to treat y as its own differentiable function of x. So just like we did when we looked at the product rule and the quotient rule, we said that u was a function of x, and therefore the derivative of u was u prime, right? It was just some extra u prime, and then we had to find the derivative of the outside. We'd look at the chain rule and all that sort of stuff. We've actually kind of done implicit differentiation without really talking about it. So what we're going to do is we're going to differentiate both sides of an equation now. Rather than just looking at the expression and differentiating the expression, we're going to look at both sides and differentiate with respect to x. That's what this is, by the way. D dx means we're differentiating with respect to x. So let's take a look at this problem here. I want to find the derivative of this function. Now, we could, yes, we could write this as y equals the positive square root of x and y equals the negative square root of x and differentiate both of those. But it's actually a little bit easier to be able to differentiate without solving for that. So we're going to look at y squared equals x, and we're going to differentiate both sides. So we're going to say, okay, what's d dx of y squared and d dx of x? Now, y squared is going to be a chain rule problem because now y is its own function of x. So it's a function that is squared. And when I square a function, I have to bring the 2 down, and I have to reduce that exponent by 1, so now I get a 1. But I have to take the derivative of the inside, which is y prime. You'll notice in the book actually uses dy dx more often than I do. I like to use y prime because it's simpler to write. So I use the chain rule. I took the 2 down, reduced the exponent by 1, but because we're differentiating with respect to x, I also have to look at y prime. And we know that the derivative of x is 1. And the whole point is to get dy dx by itself, and that's y prime. So I need to divide both sides by 2y, and therefore the derivative is 1 over 2y. And we've now differentiated implicitly. But now we need to figure out what is the slope at x equals 4. Well, this equation doesn't have any x's in it. So I need to come back here. If x is 4, what was y? Y was 2 and negative 2. Oops, sorry, y squared. Y would be 2 and negative 2, and that would be, okay, so now we can plug in 2 and negative 2, so the slopes would be 1/4 and negative 1/4. And if you recall that y squared equals x actually looks like this. And that makes sense to be at x equals 4, have two separate slopes on this particular graph. Oops, erase my pen here. What about this next problem? Finding the slope of the circle at 3, negative 4 for this particular equation. So we got a circle. It's centered at the origin. Its radius is 5. Right down here at 3, negative 4, I want to figure out what's my slope. So I'm going to take the derivative implicitly. So I'm going to take d dx and d dx and d dx. I'm going to take the derivative of the entire function, entire equation, not function. Take the derivative of x squared, I get 2x. I take the derivative of y squared. We've already done this, so we get 2y, y prime. And that's equal to, the derivative of constant is 0. And I want to know what is y prime. So I can subtract 2x and I can divide by 2y and I get negative x over y. And I want to know what is the slope of the tangent line at the point 3, negative 4. So I'm going to evaluate at the point 3, negative 4. Now I've not used this symbol too much, if ever yet this year, but this means to evaluate at. Evaluate at blank. Since it's an xy, I'm going to evaluate at this point, which means I'm going to plug it in. If I told you that y prime was equal to 3x minus 7, and I want to find it when x is 1, I would say evaluate at x equals 1. All right, so here we're going to plug this in. This tells me my slope is, okay, plugging in 3 for x and negative 4 for y, I get 3 over 4. So the slope of the tangent line to the circle at 3, negative 4 is 3/4. And that makes sense. It's a positive slope down here in quadrant 4. All right. So this big thing that we're really trying to get at is this big concept right here. Using the chain rule with a y value, not an x value. And it requires using that y prime. So it's all about chain rule and using y prime. So we want to first look at this problem. Look, it says show that the slope is defined at every point of the graph of this equation. That means you can find the derivative at every single point. So what we want to do, if we want to find the slope, that means we get to find the derivative. Finding the derivative here, if we did d dx, this is taking the derivative of the entire function or the entire equation. Take the derivative of this. The derivative of 2 times a function is just 2. And then times the derivative of the inside, which is y prime. Okay, the derivative of x squared is just 2x. We're taking it with respect to x. And then we have to take the derivative of sine of y. Okay, so the derivative of the outside function, which is sine, the derivative of that is cosine of y times the derivative of the inside. The inside is y, so the derivative of the inside is y prime. Well, now we need to solve for y prime. We need to be able to show that this equation works always for every value of x, or every point, every value of x, same thing. So I need to get the y primes to the same side. So I need to go 2y prime minus y prime cosine y equals 2x. Factor out the y prime. and get y prime by itself. So I get y prime, or the derivative of y, is equal to 2x all over 2 minus cosine of y. Now, you might be asking yourself, well, how do I prove that this has a defined slope at every single point? Well, basically, the numerator doesn't make a big difference. It all comes down to the denominator. Does this ever equal 0? And the answer should automatically be no. Because cosine has a range from -1 to 1, this denominator will never be 0, and therefore is defined at every single point. So this is my derivative, and this, because the denominator never is never 0, that means it shows that the slope is defined at every point on the graph. Another one here. Let's find the tangent and the normal line to this ellipse at the point -1, 2. Now, depending on what you want to do, there's not actually much we want to do. We want to find the derivative because we need to find the slope. Well, slope is really important for tangent and for normal, obviously. And we already have the coordinate that it goes through. So you have some ellipse, and out here at -1, 2, you have a tangent line and a normal line. So we need to find the derivative. So we need to do the derivative of each piece and solve for y prime. Okay, so the derivative of x squared is 2x. That one's simple. The derivative of x times y, and now I use multiplication because that becomes a product rule. So x times y, the derivative of the first term is 1 times the second term, plus the derivative of the second term, which is just y prime, times the first, which is x, plus the derivative of y squared, we said is 2y, y prime, is equal to 0. Now, just like that last problem, we want to get all the y primes by themselves. So I have let's subtract 2x to that side. So I get a minus 2x. Let's add y to the other side. So I get y minus 2x. Right? Because this becomes a minus y prime x, or xy prime, however you want to write it. So now I have a 2y y prime minus x y prime. And again, I'm going to factor out the y prime. And I'm going to get y prime by itself. Okay, and then I need to find the slope. So I'm going to evaluate at the point -1, 2. So I'm going to plug in 2 for y, -1 for x, 2 for y, and -1 for x. And I get a slope of 4/5. And then it's pretty simple to find the tangent line. The tangent line is going to be y equals 4/5 times x plus 1 minus or plus 2. And the normal line is going to be almost exactly the same thing, except for with a perpendicular slope of -5/4 times x plus 1 plus 2. So notice tangent lines and normal lines, same thing as before. That should be pretty obvious. Finding the slopes, the new stuff because of the implicit differentiation. And I'm going to leave us off with this problem here. This will be our last problem of the video. I want to find this thing right here, which you need to remember vertically looks like this, by the way, d squared y over dx squared, which means the second derivative. Remember that. If you put the 2 there, it's a second derivative. If you put the 3 there, it's a third derivative, all that sort of fun stuff. So let's go ahead and find the first derivative. So we need to do d dx and d dx and d dx. We got to find the first derivative first in order to find the second, right? So the first one is going to be a 6x squared. That one's pretty easy. The next one, because it's a y, I need to find the derivative of the outside function first, which would be the power rule. So 6y, reduce the exponent by 1, times the derivative of the inside function, which is y, and therefore I need to write it as a y prime. Equals 0. Pretty straightforward. Get y prime by itself. So y prime is equal to, okay, subtract 6x squared, divide by negative 6y. I get x squared over y. Well, that's only the first derivative. Now we need to find the second derivative. So the second derivative is going to be y double prime. And now since I have y prime equals this function, I can just find the second derivative. And that's a quotient, so I have to use the quotient rule. So it's the derivative of the top times the bottom minus the derivative of the bottom, which is y prime, times the top, all over bottom squared. Now, we have to do some extra stuff here because I can't use an equation for y double prime with the equation of y prime in it. But I know what y prime is. So here's what I want to do. I want to first split this fraction apart. So I got 2xy over y squared. So I get 2x over y minus x squared over y squared times y prime. But y prime is actually x squared over y. So my final derivative, y double prime, is going to be 2x over y minus x to the fourth over y cubed. We get our final answer, and you have a second derivative of an implicit function. Also should make note here that y cannot be 0. The function y cannot be 0. That should be obvious. All right, I'm going to leave you guys with that. You guys have your assignment sheet. You have everything you guys need. I will see you guys tomorrow.